Hello, my name is Pi, and today I'm gonna talk about some examples based on the previous clip that I talked about formulation. So today I'm gonna teach you how to translate some word problems, some engineering problems to optimal controls formulation. Okay, so let's start with some simple example like precision table. Let's say that you obtain this dynamic differential equation my double dot equal to negative b y dot minus ky plus u, and it's a very simple system. You say, oh, it's a joke. I solved this system since I took controls in my undergrad year, but I bet you never try to do with this kind of optimal controls aspect. Okay, so you might be able to use PID, but how do you know that PID has the right tune? So today I'm going to teach you how to formulate that kind of problem. Let's say that you want your terminal time to be 2 seconds, whatever. And let's change this to state space first. Okay. And I'll skip all the details and say that x1, okay, x1 is equal to y and x2 equal to y dot. Okay, so that I got this x1 dot and x2 dot equal to x2 on the top and negative k over m x1 minus b over m x2 plus 1 over mu. Okay, this is my dynamic system, of course. So my state x, okay, is equal to x1 and x2. Does that make sense? Okay. Now we have to figure out what is our initial condition. Okay. And let's say that this precision table start from some position 5. Okay, it can be 10, can be whatever. Let's say 5. Just some number that we can use for example. And let's say it start from the rest, right? So x2, you have to be able to see that x2 is y dot, and y dot is the speed or velocity in this case. Okay, so velocity start from the rest is 0. Position start at 5. Okay, and the problem is that we want the final condition of xt, okay, and this xt basically contain two values, position and velocity. Okay, so we want the position to return to original position, right? Home position 0, and we want it to stay. We want it to slow down to the point that it stop at that 0. Okay, we want the velocity at that point to be 0 as well. You don't want to, at that particular time t, you might stop at 0, but if you don't have this as 0, it will just gonna drive past. It might be 10 meters per second, at that point, and of course you should be able to tell what you need based on this control. So you have initial condition, you have the equality terminal constraint because it's an equal sign. It's, of course, depends on x and x of t. Okay, you say that you have some bounds that x of t at any point cannot exceed this bound. Okay, so precision table, of course, you can't go to 100 meters or 1,000 meters. Let's say that it starts at 5, right? Let's say the maximum is 7. It has to be less than 7. Okay, but it also has to be greater than negative 7. How about that? Okay, so 14 meters seems large, but for the sake of example, just go with me. Okay. Oh, it is a constraint. It's an inequality path constraint. We don't have any equality path constraint. But do we have terminal constraint? We have one equality terminal constraint. We have no inequality terminal constraint. Okay. So let me recap that. Equality path constraint, we don't have one, but we have inequality path constraint definitely, which is this one. Okay. Equality terminal constraint, sure, we have one, but we don't have inequality terminal constraint. No. Okay, so we have these two, and we have to figure out what's the cost function, what's the best thing to do. So of course we want the terminal to be here, the terminal condition to be here. It can reach this position in many ways, but which one is the optimal one? But we have to figure out what's that cost function, what we consider it to be optimal, right? So let's say that the cost function is nothing more than the accumulated controls input u square, and the reason why I use square is because u can be negative, right? If I just use u alone and I want to minimize that u, it will make u to be very negative, right? By setting it to square, I force this term to be positive term. So in order to minimize this, try to make u as small as possible to magnitude. Okay, if u is 0, that will be fine, but of course you can't be 0 because it have to force this x0 from 5 to 0 from 0 to 0 at time t equal to 2. Okay, so I won't add any Mayer's term because it's not important for this example. Okay, so I think we got everything to be able to write our controls formulation. Okay, let's look at this first. J equal to integral from 0 to capital T, is that what we have? So the Lagrange term, okay, is this capital L, it's nothing more than this. So Lagrange term L of x of t u of t is equal to u square. Okay, so it depends on t. This makes sense. So that's Lagrange terms. The Mayer terms, okay, is the term at the end, but you don't see any term that depends on the terminal condition. So that should be 0. The Mayer term equal to 0. So we're done with this, we're done with this. So now the next step is to figure out what's the dynamic constraint. So we have to figure out what is this f. So f of x u t. Okay, of course I ignore some of the parentheses, x of t and u of t, but I think you should know that by now. So this f of x, u, and t is going to be equal to this dynamic system that you figure out. So we have x2 negative k over m x1 minus b over m x2 plus 1 over mu. Okay, so that is our dynamic system f. Okay, it's going to help us with evaluating the trajectory x. Now we need to figure out what's the path constraint and the terminal constraint, and of course we only have inequality path constraint and equality terminal constraint. So for both equality path constraint and inequality terminal constraint, we can set these to 0. Okay, so therefore g of x u equal to 0. Okay, I use this. Okay, so you might get confused with this because, well, 0 is already equal to 0. Why do you have to set it equal to 0? I'm saying that this g here, okay, is equal to 0, so that when it's solved, it will set 0 equal to 0. Oh, that's fine. Okay, if I set to any other numbers, let's say 1 equal to 0, that will make the solver freaked out. So I need to set it equal to 0. H x of u, of course, is the inequality path constraint. It's not in the nice form, so I'm gonna write it like this: x minus 7, and this one's supposed to be minus x minus 7. Okay, why? Because I know that I will have this side, so it has to be in this form. Okay, it has to be in this form: h x 0 less than equal to 0. Okay, how can I do that? I have this equation here. Okay, I have these two of them, so you have to make it you have to turn this into two inequality constraint. You combine them. So this one you move 7 to this side, when you move x, so you have x less than equal to 7, so of course x minus 7 less than 0, and then you have negative 7 less than x for the second one. Okay, this is for the first one. For the second one, you have negative 7 less than x, therefore negative 7 minus x, of course, less than 0. That's the second one. So that's why I come up with x minus 7 negative x minus 7. Okay, so that is h function, the inequality path constraint. Okay, we're almost done. We need to figure out what is equality terminal constraint. Okay, so q of xt, capital T and capital T, and that will equal to, what would this equal to? It's nothing more than x of t, right? We say that x of t equals to 0, so this one will be x of capital T. Okay, and the last one is r. Okay, x of t. Okay, we don't have any, so you can say it's equal to 0. That's fine too. Okay, so now that you know everything, you should be able to use the toolbox to evaluate and figure out what's the optimal controls policy. Okay, thank you for watching and keep in touch.